Hello and welcome back. In this video, we're just going to work through an example of the kind of chain rule that we encountered in the last video. So in this case, right, we have a function z of two variables x and y, which each depend on the variable t. And here is my function z in terms of x and y, and then I have x and y each in terms of t. So I would like to figure out how z depends on t. What's my rate of change with respect to t? And I'd like to know at the time value pi over 4. So let's recall the tree diagram for this. Actually, I already have it up here. Let's recall the tree diagram for the situation, right? Z depends on x and y each depend on t. So if I want dz dt, I have these two terms, each with two factors. All right, so let's write that down, and then we'll calculate each of those. So dz dt, we need partial z with respect to x times dx dt plus partial z partial y times dy dt. Okay, so that means we need 4 derivatives to work with here. So let's go ahead and find those maybe up here. So partial z, partial x. So that'll be 2x, and the rest are constants. So that's done. Partial z, partial y, we'll need that. Partial z, partial y, the rest are constants, so it should just be minus 6y. And then I also need my dx dt and my dy dt. So dx dt is minus 2 sine t, and dy dt is 2 cosine t. Now I have all my parts, right? Everything in its place. I can put them together according to this chain rule. So that'll be what? 2x times dx dt times minus 2 sine of t plus partial z partial y, so that's minus 6y times dy dt, that's 2 cosine of t. And let's just simplify this a little bit. So I'll have minus 4x sine t minus 12y cosine of t. And there we have it. That is my derivative of z with respect to time. So now I know rate of change of, if you want to think about it like altitude with respect to time. So if this z is describing the altitude of the mountain at any point in the plane, and x and y is this is describing how I'm moving around the plane with respect to time, then this is how my altitude changes with respect to time. Right? It's very useful. Let's plug in pi over 4 into this to figure out how my altitude is changing at pi over 4. So what we'll do, dz dt, this is a function of a single variable t, and we'll evaluate it at pi over 4. So this is an interesting thing. Look, I have x's and y's here. I just said dz dt was a function of a single variable t. But here's x and y's. It looks like it's a function of 3 variables. Well, what we can do, we can go even further, because remember that x and y both depend on t. So x is 2 cosine t. So if I bring that in, I'll have what? Minus 8 cosine t sine t. And then over here, y is 2 sine t. So here I'd have minus 24 sine t cosine t. And actually, this is really nice. Some things can combine, because cosine t, sine t, these are like terms. And so we have minus 32 cosine t sine t. And that is an equivalent expression for dz dt, but just in terms of t. So now I can evaluate at pi over 4. The other way I could have done this is take pi over 4, plug it into both x and y to find out what x is at pi over 4, right? Figure out x of pi over 4, figure out y of pi over 4, and then input those in for x and y here, as along with pi over 4 for t in each of those. Or we can do it like we did here, take x and y, substitute these equations in, and just get a function of a single variable t. Either way works fine. So here we'll have minus 32 times cosine pi over 4 times sine pi over 4. Sine of pi over 4, cosine pi over 4, each of those is square root of 2 over 2. And so that's square root of 2 over 2 squared. So that'll be 1/2. And so this is minus 16. So let's interpret that result. My altitude, or my variable z is changing, my instantaneous rate of change of z is minus 16 at time pi over 4. So I'd be going downward, thinking about it like the mountain again, I'd be moving downward, I'd be descending the mountain at this time at a rate of minus 16, and whatever I'm measuring z and t in. All right, that's it for this video. I'll see you next time.